Thank you very much. Good morning, everybody. So indeed, it's my great pleasure to be here. Not the first time in Warsaw, not the first time at this university, but every time I'm coming here, I'm really impressed how much, what is the infrastructure of physics, both in Krakow, in Warsaw, and now we should try to match our scientific results to the standards of the infrastructure. And in a sense, I'm sorry I will not deliver the standard talk. I appreciate the Blackboard talks very much. But now I had only time for 2 talks. You will see there will be a break, I hope, after 1 hour. And therefore, it will be kind of overview. Maybe some of you attended the great talk of Thomas yesterday. So my talk will be also related, I hope, to make some broader overview over the topic of chaos, quantum and complexity. And then let me mention a part of this. I will not talk too much about own results, recent results, but there will be a part devoted to recent results, so I will mention only my collaborators, Rafał Bistroń, Michał Eckstein, Tomasz Miller, Wojciech Słomczyński from Krakow, also Adam Sowiński, and Shmuel Friedland from Illinois, from USA. Well, what is chaos? What is complexity? By the way, here, let me use this part of Blackboard. Let's take some letters from this formula. T, I'm just putting some letters. Yes, this is exactly this formula. And let's assume Y, G, O, E. So we understand this is a mathematical formula. But if you take any person from the street and give them such a sequence of letters, and we'll ask him, is it a complex code? Is there any meaning behind this? It's very likely he will not know. He will not know possibly this formula, the understanding of it. So for him, such it will be a random choice of letters. Even G, O, E, he will not know. Sorry, this is U, yes? G, O, E? No. Yeah, sorry. Okay, so you see, for us it means, for you it means something. But for other people, it may not mean something. And now the question, whether such a sequence is complex or not, in a sense, sometimes it depends on the insider knowledge. For you, it's not a random sequence. For us, I hope also not, but for some people it might be, if they do not know something what is behind the scene. Now a question, do I have a pointer here? Yes, this is one. Let's see. It works like this. Sorry. Yes, sure. If we have one particle, sorry, so it doesn't work, yes?
For now it doesn't.
Okay. Ale co, album pracuje z tym komputerem drugim, tak? Więc dlatego się pytałem, czy nie użyłem tego. Ale wszystkiego, dobrze. Usually we start teaching physics giving us simple problems like one particle in the potential, or here is almost a potential, in a one-dimensional potential. Well, there's a color. Look, I will try to make a recycling to use some of the pictures. Let's assume it is now, V of x, a potential well, and you have a particle. This is like first, second year problem. So we have a Hamiltonian, we have potential, and there is one-dimensional system. It's typically, always, in fact, integrable. You can predict trajectory for, in principle, arbitrarily long time. If you have two-dimensional object, if they are not coupled, if you have now V of x, y, if there is no coupling between if it separates, let's say V1 of x, V2 of y, the system is still regular. But typically, if this potential cannot be factorized like this, then it's enough to have two-dimensional degrees of freedom, very simple system. So one particle in two-dimensional degrees of freedom to produce a chaotic, unstable dynamics. So chaotic means that if you start with two close trajectories, then the distance between trajectories increases, in fact, not only in this configuration space, but in the phase space. And now you define this Lyapunov exponent. I will produce the definition later on. I'm sure you know the concept, which tells you how fast those two neighboring trajectories go apart in time. And basically, after first, second years of physics study, students may think that typical systems are regular because they only are given problems which they can solve, and you get integrable motion and integrable dynamics. But the opposite is true. A generic system is enough to have two, let's say, degrees of freedom coupled enough, and they will typically produce non-integrable dynamics, non-integrable motion, difficult to predict with positive Lyapunov exponent. So yesterday, Tomasz mentioned the name of Chirikov map. I had a pleasure to meet Boris Chirikov many years ago, and really the map is a very simple transformation, let's say, of a square into a square, or maybe of a torus into torus. So you have x and p, and you see the map. It's two-dimensional map, and the only parameter is k. And now, depending on the value of k, different kind, here it is. Thank you very much. Great, it works. It's red, yes.
There's green also.
Okay, no, great. So, if k is 0, you have just a rotation. So, this is dynamics in this square. So, for k equals 0, you have just lines. So, in fact, you have points. All those points which eventually, for typical not commensurate initial point, will produce a line. Because it's just a rotation. So in a sense, x or theta is like a phase, and p is like a somehow momentum. Now, if k grows, the situation changes. You observe appearance of some resonances. This is main resonance, 2-to-1 resonance, 3 resonance, and so on. And there are still some tori which are still not broken. They are called KAM for Kolmogorov-Arnold-Moser tori, and then there appears like here, the chaotic layer, chaotic dynamics. You see those points are not ordered. So one trajectory is many points, but they form such a strange chaotic layer. But if this kicking strength K parameter is smaller than some critical value of order of unity, then the chaotic dynamics is still restricted to one layer or second layer. Only after, if K is larger than the critical value, the last KM torus is broken, and then we say that the chaos is not bounded. You have the chaotic trajectory can basically explore entire phase space. For k of order 2, you still have some islands here. Even for k equals 5, you can see some small stability islands around some periodic orbits, but the majority of the phase space is covered by a chaotic trajectory, so Lyapunov exponent will be positive. By the way, technically, Lyapunov exponent will depend on the position, but if you have one chaotic layer, then this largest Lyapunov exponent will be typically the same. Largest because the number of Lyapunov exponents depends on the dimensionality of the system. In this case, we will have 2. Well, here's another similar picture, but now in color. So here is again a kind of mixed, most interesting, in some sense most complex case. K is smaller than 1, or 6, so you still have resonances, but the dynamics is complicated. Here already is K is over 1, so this light green trajectory basically is, you have a connected chaos. You might have a diffusion in the momentum, so there are no KAM tori, and you see many resonances of higher and higher order. In fact, the structure is kind of self-similar. So you, if you look closely, you can find many smaller resonances which correspond to higher order resonances. Here is of order k is equal to 2, and eventually we can see in such a simple map, called now standard map, a transition from regular motion to fully chaotic motion. This is everything classical. So let me remind you again the more formal, still not mathematically rigorous definition. So we take basically point x, now we add some small perturbation, we iterate the map t times, and we check how the difference scales with time. So we compute limits that perturbation goes to 0, and later t goes to infinity. Here is of course 1 over t. By the way, those two limits do not commute, and this is in some sense, so here we have some mathematicians around, so of course it's not a fully mathematical definition, but this will somehow lead typically for largest Lyapunov exponent. Typically because it means that you can if you are unlucky, you can choose such a perturbation for which this quantity will not give you Lyapunov exponent, but it will be bound for Lyapunov exponent. And the most important thing is, well, people ask us, let's say not us, but we can ask, and now we ask Google or our cellular phone, what will be the, let's say, weather tomorrow, what will be temperature. So we are asking about predictions. And of course it's easier to predict the weather for tomorrow or today than in 1 year. And the typical here prediction time is related to Lyapunov exponent. So in a sense there's a notion of Lyapunov time. Yes, it is just inverse of Lyapunov exponent. The larger Lyapunov exponent, then the shorter is the time you can predict the dynamics. So here I put some data taking from the Wikipedia. So for solar system, by the way, is solar system regular? Is it a regular system or not? Who knows? Maybe you know that Poincaré studied this problem, and we have somebody from Sweden. Who is from Sweden here? Why I'm asking about Sweden? In Sweden they had some clever kings. Oscar was his name, yes? You know, who knows the story? So now politicians, presidents are not so much interested in science. And many years ago, King Oscar, yes, it was Oscar II, please correct me, he was clever enough, okay, of course he had some good advisors, and he founded a competition to discuss the problem of stability of motion of solar system. And then Poincaré, there were several really famous scientists took part in the competition, and then nobody technically solved the problem, but Poincaré was the closest, and he won the prize. So Poincaré, you recall, he was also studying free body problem. He basically showed that if you have three bodies of the similar mass, then basically in such a simple system, the motion will not be integrable. So if you had only Sun and Earth, everything will be integrable. But it's enough to have Jupiter and Saturn to create to induce non-regular component, but of course this Lyapunov exponent is very small, Lyapunov time is very large, so here's estimation 5 millions, some other people say 10 millions. So if you wish to make an appointment for tomorrow or next week, you can still do it. So the Lyapunov time is so long for our solar system that we don't need to be afraid of it, yes? We can allow sun or solar system to maybe even disappear after some millions of years. And maybe you have heard about Hyperion. It's a kind of a moon of a Saturn, which is very strange. Why it is strange? Because it's not a typical moon. Well, it's like ellipsoid or a ball. And Hyperion is like a potato. It's very elongated, and it is, in some sense, best known object because of the classical mechanics. It produces some strange dynamics because of the momentum, and therefore the rotation of this object around Saturn is described by Lyapunov time of order of 1 month. We have famous chemical reactions. I think that's called Bielousov-Zhabotynsky reaction, and then the time is like a round of minutes. For hydrodynamic oscillations like seconds. And here somebody found that for 1 centimeter, it's like statistical physics of a gas in room temperature, this Lyapunov time is of order of 10 to minus 10 or 11. So basically you cannot predict the dynamics of a 1 centimeter of gas for longer times. And in principle, the shorter Lyapunov time, the more unpredictable and complex dynamical system we describe. And in principle, limiting case T going to 0, so lambda to infinity, would correspond to random sequences where you cannot predict the future at all. This is the definition of randomness. By the way, if you have like this, a sequence of letters, of numbers, let's say I have another sequence of numbers, whatever, let's say 0011, 0011, 1110, and so on, you can never prove that such a sequence is random. Just to opposite, you can say, I realize it's not random because this and this it does not satisfy some properties a random sequence would display. But it's not like this that you can confirm, this is really a random sequence. So in a sense, this notion of randomness is kind of in a bit elusive and defined in an apophatic way. Apophatic means I only know how this object does not look like. I cannot say this is really a random sequence unless I, well, produce it myself. Another important example is famous logistic map. So this is extremely simple dynamical system, one-dimensional dynamical system. We map interval into interval, 0, 1 into 0, 1. Therefore, A has to be smaller than 4. And what happens? Here is the famous bifurcation diagram. It's related to famous Feigenbaum constant. Basically, if A is of order of 2, you have only stable point. Then there is a bifurcation. Here you see at the same axis Lyapunov exponent. So here it touches 0, then it is still negative. Then there is another bifurcation. So the Lyapunov exponent is 0, then another bifurcation. So the Feigenbaum constant, there are a few, it's just the ratio. He showed that there was a universal ratio between, let's say, difference in this parameter and in this parameter, and if you compare subsequent, there is an infinite sequence of those bifurcations, and then it displays some universal properties, and eventually there's a critical value, some 3.6 something, and then the motion is already chaotic, so then the Lyapunov exponent goes positive. But now you see here somehow it goes down. It goes down because you see here there are periodic orbits. This orbit 3, orbit 5, and so on. It's related to the famous Życzkowski theorem. Who knows Życzkowski theorem? You don't? So Życzkowski theorem tells you a very nice, from this picture, Życzkowski theorem is somehow coded here. It's related to the famous sentence, 3 implies chaos. Lee and York. Why? Because if you have period 3 is the last window, then on the right is, the dynamic is chaotic. So this Życzkowski is a strange but very nice sequence of numbers like 2, 4, 8, because first you have bifurcation, and from this side you have like 7, 5, 3, and all numbers are ordered in order as the sequences of periods appear in this graph. So this is nice way to show that this Lyapunov exponent, so degree of chaos, somehow is related to complexity, but it's not like this that here the case 4, Lyapunov exponent is in a sense maximal, log of 2 in this system. So here is really a random system, but some people believe that even this case where Lyapunov exponent is close to 0, like here we have, look, we have here this free window, but here's another small bifurcation and so on, then the dynamics is more complex. And of course the notion of complexity, there are many different approaches, and it's very difficult to say, looking even at this picture, at which value of this parameter the motion is most complicated to describe. However, if you know the formula, you can say the description is simple. I will mention Kolmogorov complexity very soon. So a recipe to write such an equation is very simple. I can write you, let's take such an equation, set A, let's say 3.9, and let's look for instance, invariant density. So then the object, this invariant density, which apparently looks very complicated, can be written in a very simple way. So let me make a short introduction. So I'm afraid you know perhaps a lot of all of this, but I think it's good to have some historical background. So, okay, I can only say that for me, the science about complexity is complex. In a sense, it's not easy even to enumerate all important contributions. So there's one notion of Weaver 48, and he distinguished disorganized complexity, like large systems, for instance, container with gas, let's say 10 to 6, for him was million, but could be, let's say, number of Avogadro and whatever. And of course, the dynamics will be very complicated. And he also distinguished organized complexity, if you have correlated interaction. And for me, those examples of deterministic chaos, they are usually related to this organized complexity, because even though there are not many degrees of freedom, because of the coupling, interaction between them, the dynamics is apparently very, very complicated. And we know, perhaps you also know the name of Kolmogorov and Kolmogorov complexity, but before his papers, you know how he was doing in Russia, so there was not such a good interaction those days, or like now, between Russia and US. So maybe those papers of Bloom were not known. So Bloom was, I think, one of the first in '67. He was discussing computational complexity, but perhaps he was not was unaware of earlier paper of Kolmogorov. But the idea is, in a sense, similar. Idea is to measure complexity by the, let's say, recipe how to produce the sequence. So technically, you can always define the descriptive complexity of an object like text or picture or even piece of music as a length of the shortest program that produces such an output. Which is nice, but it's implicit. So basically, if you have such a sequence of letters or a picture, and you do not know how it was produced, it's very difficult to guess, is complexity high or low? Here I will also mention names of Solomonov and Chaitin. Chaitin, there's a famous Chaitin number. Okay, so there are really people who did a lot concerning computer science and complexity. So the simple example of, in principle, complex object is a random sequence of some number. If I claim that I tossed my coin 10 times and I produced such a sequence, some zeros, some ones, head or tails, there is no other option as to enumerate all those numbers. So then you cannot make any compression. So in this sense, such a really random sequence is random, unless it's really random. Because if it was produced by random number generator, like a pseudo number, a pseudo random sequence, then of course the procedure or description can be much shorter. By the way, if you wish to ask something or something is not clear, I am too fast, so please do not hesitate to break. Yes, ask question, please.
I think like this description is maybe not kind of confusing about this like length of the shortest computer program, because for example we have high C++ like languages like the Java or something, and we have like that they are closer to like machine language.
Yes, sure. Okay, but let's say the number of bits you say, you can, the optimal number of bits you need to encode such a sequence, yes? But of course it's only, let's say, idealistic mathematical definition, not easy to use in practice. So okay, shortest program, of course, you can say the shortest number of bits which allow you, or you can send to your colleague to produce a given sequence. And of course, it's clear that if those numbers are really random, and there was no mechanism behind it, there's no other option as to send all those bits one after another. So then it's not compressible. So in some sense, the question of complexity, this descriptive complexity is related to the compressibility, how much the sequence can be compressed. And now look, let me give you some example like this. Is this picture complex or not? How do you think? So, how do you think?
No.
It's not. I like this picture very much, and you think it's not complex. But okay, you can ask one question, is it whether it's nice, and second, whether it's complex. Yes, there are two different questions. Well, you are right. It's not a complex picture, even though I like it very much. I like it because it's our picture. So, it was the invariant set of parabolic map of the square. So map is very simple. We start iterating points which were distributed randomly in the square, do it many times, not so many, it's enough 100, and you get such a picture. So to describe this system is very simple. You write such an equation, and you say, do it 100 times, starting with 1 million random points. But the result is kind of maybe non-trivial in a sense, but it's trivial if you know the formula. But of course, if you are given such a picture and you don't use Google or artificial intelligence to find this paper, it will be difficult to reproduce it from your own, by your own. By the way, is this picture complex? But maybe you know. For you, maybe not, because you can recognize some shape, yes? But to produce especially this, so you can guess. Now I will tell you a story. This is an invariant set of some dynamical system, and this is invariant measure. You see? Measure is, of course, supported on this set, but it has non-trivial density. So this is even more complex than this. And again, it looks complex, but it's not. Because it is, in fact, invariant set, invariant measure of some, it's called in mathematics, iterated function systems. There are 13, but important, linear maps. There are linear maps which map square into square, but in fact, inside. And this is invariant set, invariant measure, which was produced, in fact, only 6 iterations were needed to get this. It's enough, okay, after 10 iterations, the changes are very, very small. So it's amazing that so fast you get convergence to equilibrium. So the joke is, of course, okay, it was published with my student many years ago. And who of you will know this date? A historical question. Wow. Okay, I'm old enough to remember. So maybe you know that Poland joined European Union in 2004. But there were the Treaty of Athens in 2003, as officially it was decided that Poland will join the European Union. So I was thinking, in this paper we use the name of Euro attractor. The idea is of iterated function system that for any initial density, everything converges to this invariant density. As you see now, the history is more complicated, complex, you cannot predict it. So it is not as simple, but then somehow we were very much enthusiastic. Oh, we still are. Well, and this was like example that with very simple means you can produce such a shapes, whatever you wish. So again, knowing those equations, it's very simple, and then this complexity of this apparently complex picture is very low. This is the example I already discussed. So you can see such a probability density. In fact, it's an approximation of a measure. So here is axis from 0 to 1. Blue is like density, which in fact will be fractal. And again, it looks complicated. But it's not, because this is exactly the invariant measure of this famous logistic map obtained for A equal to what? 3.8. So the description is very simple. Take this map, take million of points from 0 to 1, iterate them, let's say, 100 times, in fact 20 is enough, and plot the density. And again, this density has very nice mathematically complicated fractal structure, but knowing the formula, it is very simple to reproduce it. And of course, this measure changes with parameter A. If you change A here a little bit, the shape will be, of course, different. And here you see it's supported from this point to this point, so it doesn't cover entire interval. In a sense, I can show you, go back to this famous Feigenbaum picture, because here, let me only remind 3.8. If I go here, then you can say, I take cross-section here at 3.8, maybe here. It was done like this. And you see how many black points you will find along this axis. And you see the support is smaller than the entire interval. So this is the idea of these red lines here. So in a sense, this picture is kind of encoded in this famous bifurcation diagram of Feigenbaum. Well, another famous picture, Mandelbrot set. So this is, by the way, a simple question. Who discovered Mandelbrot set? Of course, not Mandelbrot. This would be too simple. It was discovered by Brooks and Matelski in 1978. And they had the first computer picture of it, but not good enough. And Mandelbrot, of course, came and made a great story out of it. So he discovered self-similarity, and Mandelbrot was first to realize that he had already better computer. That if you magnify this amazing self-similar structure, and basically this complicated, apparently very complicated structure can be explored and discovered if you magnify some parts of it. So formally, technically speaking, you have a map which maps complex plane into itself, very simple. Z goes into Z squared plus C, and this is the complex plane of C, and black means that this map will not diverge to infinity. If the blue point means it will diverge. And this is such a definition. In fact, it's related to logistic map, as it was discovered later on. So logistic map and this map somehow, even though they are extremely simple, it's like parabolic map, second order quadratic map, it describes very complicated and apparently complex dynamics. Well, so I will make a short recapitulation of the classical case, because in principle we'll go to quantum soon. So if we have a classically chaotic system, like this logistic map, or Chirikov standard map of many other maps, then they are chaotic because, technically speaking, this largest Lyapunov exponent is positive. There is also this Kolmogorov-Sinai dynamical entropy, which was also discussed yesterday and today. It's of course related somehow. There is this famous Pessin theorem, which basically tells you that this quantity, which has the meaning dynamical entropy, means its derivative of entropy, its production of entropy, its change of entropy in time. Its Pessin theorem tells us that under some technical mathematical assumptions, it's equal to the sum of all positive Lyapunov exponents for a many-dimensional system. If system is one-dimensional, they are just equal. So this is the case for the logistic equation. So for such systems, the dynamics produced can look apparently random, apparently very complex, chaotic, but the sequences will not pass all the statistical tests for randomness. So if you work hard enough, you can basically show it's not a random sequence, even though it looks like a random. So you see the point. If you see such a sequence and you don't know it's produced by, let's say, logistic map for such and such initial condition, it's difficult to say that the complexity is low. So, in short, it is not possible to state that a given sequence is really random. It can only be shown that first, if it's not random, you can try to find some properties a random sequence should satisfy, and given sequence does not satisfy. And if it fails if it satisfies all those tests, then you can believe that it might be a random sequence, and you can use it, let's say, as a random numbers generator. In fact, we do not have good random numbers generators. We have a lot of pseudo-random generators, which pretend to produce random numbers, and sometimes they are good enough. And I think here is a very nice quotation of John von Neumann. You will know the name. Look, anyone who considers arithmetical methods of producing random digits is, of course, in a state of sin. Isn't it nice? Look, there is a bit catch here, because it means that in a deterministic way, it's difficult to produce pseudo-random numbers generators. But of course, you can say, my computer does it. My computer does it every day. So what is the catch? The good computers, they will not start from the same seed. So they can use time as a seed. And here it's written in a deterministic way. But of course, if you have nowadays a modern computer, there's many nice techniques to use, for instance, the clock, which changes, to change the seed and to generate different numbers, different sequences every time. So in a sense, the fact that we use random number generators every day is in a sense not in the contradiction with the statement of von Neumann, because those random numbers are generated with some seeds which change. Now we'll also change the topic. What can you see? Just to wake you up. Can you see somebody? Two people, two persons. They are talking. What they are talking about? Who knows? Who can guess? Complexity. About complexity, yes, almost, very well. They were talking about the Lebesgue integral. It is Otto Nikodem and Stefan Banach. They were talking at the bench in Planty Garden in Krakow. But look, summer 1916. Can you imagine? Why is this important? 16 was the just middle of the First World War. By the way, Russian army was very close to Krakow in 15, but it was expelled back to Przemyśl and then to Lviv. But still, Banach was studying in Lviv. He didn't finish his studies because of the war. And they were talking, can you hear me? At this bench, and they were talking about Lebesgue integral, and then Steinhaus, who was already PhD, he got his PhD in Göttingen, in a good place. He was passing by, And he was so much amazed that some young people are talking about such a, in a sense, new and advanced problem. So he approached them, interrupted, and started talking. And then they were very much amazed that they have a chance to meet a real mathematician. And Steinhaus apparently told them what he is working on. They met in 2 weeks, and Banach already had a solution. And then all his life, apparently, Steinhaus was repeating, he had really very good results, but he always claimed that his best discovery, mathematical discovery, was Banach himself. So I will return to this story soon, but this was like a break. So now we will go slowly to quantum case. So for you, I think quantum is the most important, but classical is kind of a good background, the theory of classical dynamical systems. And now we are going to go to quantum. There are different ways of quantize. By the way, one more thing. If you have a classical system, whatever, if you want to quantize it, there are many different ways to do it. It's not a unique procedure. It's not like this that somebody gives you a quantization and this is the best, only possible quantization. Another person can find other quantum system which can be considered as a quantization in the following sense. If you go to well-defined classical limit, you should get back this classical system. But going from classical to quantum is interesting, nice, but not unique. So in principle, we can have like dynamical systems, and quantum system will be described, for instance, by a Hamiltonian. So here we prefer to have finite matrices. Of course, the dimension of this matrix can go to infinity, and then you can have unitary dynamics, like exponent of the unitary of the Hermitian matrix is unitary. T is the time, is just the parameter. Of course, a physics student will ask where h bar is here. Okay, it should be. It's just a constant. For mathematicians, not important. And then, if in general, rule of thumb, if this classical dynamics is kind of regular, then this Hamiltonian matrix could be or will be typically will have some structure, which is not the case for really chaotic dynamics. Then important thing is if we have not one system but two systems, like composed system, you have complex composite Hilbert space, like for instance tensor product, and you can speak about entanglement. By the way, there was a talk about entanglement today, yes, so to have entanglement you need to have at least two systems. And you have to compute, let's say, partial trace over one subsystem. So the idea of entanglement has only sense, physically speaking, if you define two subsystems, one and second. If you have a complicated object without specification, which is the first part, which is the second, you cannot talk about entanglement. So here we say that this physical system is described in this tensor, mathematically speaking, in the Hilbert space with the tensor product structure. There was a nice introduction to this field yesterday by Thomas, so I will only mention here the relation to random matrices and the idea of quantum chaology in the following sense. Classically, we can define classical chaos by assuming that all Lyapunov exponent, all dynamical entropy is positive. In quantum case, it's not so simple. In fact, even now, 40 years later, there are still disputes how to define quantum chaos, and therefore the famous person, I should say Sir Michael Berry, this is true. He got the, how is it called? Nobelity for his discoveries also. In the UK, he is in Bristol. Sir Michael, he was using such a notion, quantum chaology. Not, okay, quantum chaos, but chaology, what he was thinking about was the science to discuss properties of quantum systems which correspond to classically chaotic systems. Those are well defined. So therefore this name chaology, I think is nice, science about such systems without defining them very precisely. And the main observation was that those analogs, I would say, of classically chaotic dynamics can be described by ensembles of random matrices. And for autonomous systems, if you have Hermitian Hamiltonians, one uses Gaussian ensembles of Hermitian matrices, and depending on the symmetry, one uses Gaussian orthogonal, unitary, or symplectic ensemble. So those letters means Gaussian, let's say, unitary ensemble. And they are like, for instance, coupled spins, strongly coupled. And if you have periodic systems, we have unitary evolution operators, and then people use unitary matrices, and they are called Dyson circular ensembles. and they are called circular, orthogonal, unitary, or symplectic ensemble. Dyson, because Dyson invented them. Circular, because of what? Because of what? They look like a circle? Almost. The spectrum is at the circle. So circular, because the eigenvalues of a unitary matrix is always at the circle. Therefore, the name is circular. And I will mention this nice, okay, in fact, there should be, okay, kicked rotator or kicked top. I will mention it in a second. So just to remind you, so, okay, I'm not sure. Are you aware of those notions of GUE, GOE? Okay, so I will be very, very brief. So look, Thomas yesterday was not showing any formula whatsoever. I will show some, so I will try to make some compromise. It's not easy not to show any formula at all. But the way to construct such ensemble is very simple. You have to have orthogonal ensemble. Beta is just a simple parameter which shows you what is the number of parameters in one entry. If you have a real random numbers, beta is 1. If you have complex, so real and imaginary, then you have beta is equal to 2, and symplectic ensemble corresponds to quaternions, so beta is equal to 4. And then you construct such a matrices with all those, of course they are Hermitian, so there's one symmetry, so the spectrum is real. In the last case of symplectic, the dimension is even, 2n times 2n, and then all those matrices have important property. This density or probability distribution is invariant with respect to orthogonal, here unitary or here symplectic transformation. But for a first year student, it's very simple. He doesn't even need to understand all of this. It's enough to tell him, construct matrix, put independent random numbers with normal real complex or symplectic, let's say real or complex, with 0 mean and variance you can be fixed to 1. And then this probability distribution, joint probability distribution of eigenvalues is given with such a formula, which is not so complicated. And here, this is like Gaussian term, this is like special determinant, and the beta is just this number 1, 2, and 4, and somehow this beta describes the ensemble. So of course you can diagonalize those matrices and get eigenvalues, and this is the joint probability of eigenvalues, which was computed not so many years ago, let's say 50 or 70, but not 100. It's not so new part of mathematics. And also look, the very famous statement concerning the density of such matrices is also, I realize now how many years it is now, 70 years old, yes? It's called Wigner semicircle law, 1955. So it was, the point is the following. You take such a Hermitian matrix, diagonalize it, and look at the density of eigenvalues. And then, okay, under suitable normalization, this density is very close to semicircle, therefore it's called the Wigner semicircle law. And so this is the shape of the distribution, and x denotes this normalized eigenvalue is normalized by n, and then for any n, for any dimension, this is the density. And here, important word or notion comes into play, namely universality. So look, this is independent on the dimension and also on the choice of this ensemble. The density will always be, will have such a semicircular shape. So here the most important thing is that matrices are random, so their complexity is high, but properties can be with large probability, you can say with measure close to, with measure 1, can be described. And this is kind of a nice paradox, that even though a given realization of random matrices is very complex, you cannot describe it otherwise like writing it down, we can predict its properties. So as yesterday Tomasz mentioned, it's kind of a bit order in chaos. So even though everything is random, some properties, like properties of values, density, or properties of eigenvectors are universal. And for instance, here this beta parameter describes the level spacing distribution. So S is difference between neighboring eigenvalues, For Hermitian matrices, we can concentrate on the center of the spectrum where density is flat. We can also use so-called unfolding to change it to the flat, to transform it to the flat distribution. And then P of S will behave like S to power beta. So it means that it's very unlikely that two eigenlevels will be close together. They tend to repel itself. It's called level repulsion, and degree of level repulsion is just characterized by this parameter beta. Okay, and here are those expressions of Wigner. It's called Wigner's surmise, what it means. It was derived analytically. Here you see there are densities of beta equal 1, 2, and 4, and they have the following structure: S to power beta and some Gaussian decay. And this is explicit exact analytical formula, which was derived in the case n equal 2, but strangely enough, it's not always the case. It describes well asymptotic case. So it's exact for n equal 2, but it doesn't change much with dimension, so it fits well for large matrices. So this was for the, we started with Hermitian matrices of Gaussian ensemble. But again, this universality tells us that the same situation, or similar, holds for unitary matrices, for circular ensembles of Dyson. Then the situation is simpler because density is uniform. If you have everything at the circle, density for the random Haar unitary matrix is flat. But the distribution of spacing, so spacing is just difference between, let's say, second and third eigenphase, eigenvalue, rescaled in a suitable way. Then the distribution P of S will be given by those formulas of Wigner. So we'll make a break, let's say, in 10 minutes. So, yes, just to make a break. Here is a concrete realization. It's a model similar to Chirikov map. Chirikov map sometimes is called kicked rotator. So it was a rotation and kicks, but here it's called kick top. Designed by Hake, Kusch, and Scharf. By the way, Kusch is a name some of you might know. He's our colleague and professor in Warsaw, at the Center for Theoretical Physics in Warsaw. And Hake, Professor Hake was my mentor, by the way, in Germany in Essen many years ago. So now we have dynamics, which is, we have a point on the sphere, this is the equation of the sphere. So we have a sphere, and there is a free evolution around some axis and some kicks. Evolution and kick, and there is basically this is the free evolution and this is the kick. So if the kick is here described by small k, so if k is 0, one has regular dynamics. Here k is 2, 0, 2.5, again you observe transition from regular dynamics to chaotic. Here's k equals 6, and here the evolution is already, classical evolution is chaotic. So this model is very convenient to study because you can now change kicking strength, but also dimensionality. So this is the classical model, but it's nice, very relatively simple to find the corresponding quantum model. So there are first results obtained already in 1987, so already many years ago by this group. And here we have a quantized version. So this is the Hamiltonian, which corresponds, let's say, it could be classical dynamics. So PJY, J is of course angular momentum operator, which gives you the rotation like this around given axis. And from time to time, so here you see the sequence of Dirac deltas. So it means that at the integer value of time, there is a very short, therefore it's called kick, transformation. Again, rotation and kick, and so on. And this is the formal definition of the Hamiltonian. But because you have here Dirac delta, so during this infinitely short time, during the kick, you can neglect this part, and therefore the unitary evolution operator has two parts. This is related to kicks, and this is related to the unperturbed evolution. And for regular dynamics, if k is very small, let's say, this was average from 0,1 to 0,3. One classical dynamics is practically regular, and quantum dynamics is described by unitary operators and level spacing distribution P of S, is well described by so-called Poissonian distribution. Poissonian distribution means they are almost random, not correlated numbers. And then if the kicking strike changes, here is a strongly chaotic regime from 10 to 10.5, you have level repulsion, so P of S is very small. There is no large probability to observe that level cross, which was also mentioned yesterday. And for different classes of symmetry, you have orthogonal or unitary ensemble. Those two curves correspond to those Wigner distributions for beta equal 1 and 2. So I think I will show you this picture of late Fritz Hacker. He passed away some 5 years ago. And he was known not only because of his nice papers and books. He wrote famous book Quantum Signatures of Chaos, which had 1, 2, 3, 4 editions. And then interestingly, the last edition, which was ready just before he passed away, was written already together with Marek Kuś and Sven Gnutzman. So Marek is now co-author of the last edition of this book, where somehow quantum chaology and the relation to random matrices is well described, and most importantly, relation to the theory of periodic orbits. I will not mention today, but it's a very good book. I can really recommend you. So here is a short recapitulation of this part concerning unitary dynamics and Kick-Top as a model. So if the motion is classically regular, the eigenvalues of unitary evolution operator are not correlated, and level spacing distribution displays level clustering, and the distribution is Poissonian. On the other hand, if the dynamics is already classically chaotic, so the kicking strength is strong enough, then this level spacing distribution P of S displays level repulsion is described by Wigner distribution, and interestingly, it's universal. So it doesn't depend on the details of the model. So if the classical dynamics is already chaotic enough, the quantum unitary, in principle, it looks complicated, looks apparently random. In fact, it's not random, it's pseudo-random. But the statistical properties are very close to those predicted by the theory of random matrices. And for instance, eigenvectors are delocalized. So here is this famous conjecture or observation. It's not a mathematical theorem. It's a statement that of Bohigas, Giannoni, and Schmidt from 1984. Yes. How is it? No. Please remind me. So, who knows Orwell? What was his year? 84, yes? So no, and I realized how I knew that such a name is kind of interesting. Yeah. But it was, I don't think it was correlated. It was an accident. That in this year, they had this conjecture, because of course Orwell wrote it like 40 years earlier. Yes, for him, 84 was already a long time in future. So in 84, they had an important paper, and they first observed that under a condition of classical chaos, quantum dynamics has some universal features which can be easily predicted. And this was, indeed, it's not even possible to give mathematically rigorous assumptions. But typically it is so, and still many people try to somehow work out and make this conjecture more precise. And it's good to somehow see when and under what conditions this statement is true. Well, yes, so I think I will finish with this story, and then we'll have a break. So what can you see? So those of you who are, so there's at least one colleague from Krakow, he will recognize this. This is the Wawel Castle in Krakow, yes? So who of you has seen this place? Okay, at least one, so I also, but yes. Okay, there are a few. Well, so picture like picture, I think it's a nice picture. But now look, is this picture, could it be used as a help to formulate some mathematically rigorous statement? A theorem. So I will try. So there will be a theorem of Danuta and Krzysztof Ciesielscy, my colleagues from mathematicians from Krakow. But to formulate it, look here what I added such a red arrow. You see it? It's critical for this point. Because the statement is, this is the theorem of Ciesielscy in full glory. for any epsilon larger than 0, there exists eta larger than 0, such that with probability 1 minus epsilon, the bench Banach talked to Nicodem in 1916 was localized in eta neighborhood of this set R. You see a very rigorous statement. It is not easy to find the functional dependence between those constants, but so it is. And now, possibly because of this, in this very place, there is now small bench, and which memorizes this meeting of Banach, Nicodem, and Steinhaus. So here is a larger text in Polish. I will read this shorter in English. Otto Nicodem here and Stefan Banach in conversation about mathematics. This bench memorizes their famous meeting with Hugo Steinhaus in the planted garden in summer 1916. So I was asking, who of you knows